Okay, so we are now on the carbocation stability and the occurrence of molecular rearrangement. No? So again, I have already mentioned earlier, no, when we have predicted on the, since nakat, no, we have predicted on the reaction of this one, no, when you have your leaving group, the OH, we're supposed to get a double bond somewhere here, no, but in the product of this reaction, we never get a 1 degree alkene in this case. No? So let's look at on the what happened in between, why we get this product instead of what we should get as 1 degree, or yeah, one or a monosubstituted alkene. Okay, so similar to what we have in the E1 mechanism, so rearrangement happens only in the E1 mechanism. Okay, so this is in the E1 mechanism. So the first step again always is the protonation of the alcohol. You know how that happens. The second one is once you have protonated alcohol, here you have your OH2 plus, ganong plus na siya. Of course, oxygen has 3 bonds and an electron pair. So to relieve that positive charge, it's easy for H2O to leave, or the OH to leave. No? And then you get your carbocation. Now your carbocation here is a 2-degree carbocation. Now the arrangement, of course, the less stable secondary carbocation rearrangement to a more stable tertiary carbocation. So this is a 2-degree carbocation, but adjacent to that is a 3-degree carbon, no, and there is a CH3 group attached to this. So what happened here is the shift of the methyl group, no, to stabilize this 2-degree carbocation. We've learned that a 3-degree carbocation is much more stable than a 2-degree or a 1-degree. So to do that, to increase or to stabilize this 2-degree carbocation, which is very unstable, no? So there is what we call as a methyl shift. The methyl group will shift to here, and that we will actually obtain a positive 3-degree carbocation. Okay, so you notice in the red is shifted here, and so in effect you have a 3-degree carbocation being formed, and this one is much more stable than the 2-degree carbocation. So the transition state in between to produce our 3-degree carbocation from a 2-degree carbocation, you have this. There is a partial bond formation between this positive carbon and CH3, and a partial bond breaking process between CH3 and this beta carbon here. Okay, so this is the transition states being formed, and we get a 3-degree carbocation. So from the 3-degree carbocation, then we can do now, since this is much more stable than the 2-degree, then it's easy now, can now proceed with the elimination. The base will now abstract our beta proton. So this is our beta, or this is our positive carbon. So there are many options for which your base can abstract. It can abstract this beta hydrogen here. It can abstract the beta hydrogen, either of this, no pariharesia. And of course, as we've learned that in the elimination reaction, it favors, it follows the Zaitsev rule, unless of course we use a bulky base. In the Zaitsev rule, the more highly substituted our alkenes are, the more stable our alkene, and the transition state that leads to the formation of the alkene. Okay, by the way, we call this one shift of our methyl group to be a methanide shift. Now, when it shifts, it brings with it its pair of electrons. Now, silingan naman siya, adjacent naman siya. You always have to remember that this one is p unhybridized orbital, and this is an sp3 carbon here, and sp3 also carbon. So it brings with it its sp3 by overlapping here, and shifts towards here, you know, the 109.5 degree here. It's very close to the close to being parallel to unhybridized p here. Same with what we have learned with the hyperconjugation. No? So you have this 3-degree carbocation. From the 3-degree carbocation, then we can use our base to abstract our beta proton. So you have mentioned earlier or base can obstruct this beta hydrogen here. Beta gani kadong alpha. These are the positive charge carbon will be our alpha and beta, no, carbon, and the hydrogen attached to your beta carbon is beta hydrogen. So you have two kinds of beta hydrogen. You have this and you have this. So let's say we abstract this blue hydrogen here. To get the blue hydrogen, we actually get this double bond here. So let's say you have your base, hypothetical base A with an electron pair sa iyaha and a negative charge to be a strong base. So it's abstract the proton here. It uses its lone pair to abstract the proton. Okay, so since it uses its lone pair paingon sa proton, proton will not bring with it its electron pair, but it will leave its electron pair to form a double bond here. So you get your double bond here. And so you have your CH3, CH3, double bond from here, and CH3, CH3. Now, if the base will abstract this red pink proton, okay, what happens is, okay, it again utilizes its lone pair to form a bond with hydrogen here, proton here. And what happens is that since it utilizes its lone pair, the electrons beacons a bond will be utilized to form a bond here, a double bond to stabilize this positive charge. No? So you will get your CH2 double bond. Okay, you have your CH3, and then dash, you have your CH, CH3, CH3. And looking from the structure, this one is a 2-degree substituted alkene or a di-substituted alkene. You have one group, another group. This one, you have a tetra substituted alkene. I hope maklaro pa ko. Saba kayo mga manok. You have a tetra substituted alkene. You have 1, 2, 3, 4. And again, according to Zaitsev rule, formation of the more stable alkene is the general rule in the acid catalyzed dehydration of alcohol. So what is the more stable alkene, the most stable one? The one that is highly substituted. So between this B and this A product, you expect this B to be the major product other than A. And in the end, no, we don't get the one that we predicted earlier. Katong supposedly dinhi ang double bond. Okay, so instead what we get are two kinds of alkene. Okay. So what are the things so studies of many reactions involving carbocations carbocation ions show that rearrangement like those just described, it's a general phenomena, and they occur almost invariably when alkanide shift or hydride shift that can lead to a more stable carbocation. So it's not just a methyl for a methanide shift, it can also be a hydride shift, no? Whenever there is a possibility for a 2-degree carbocation to lead to a 3-degree carbocation. So for example, here, what we have just described from a 2-degree carbocation, there is a shift of the methyl to do our 3-degree carbocation. Methyl is much smaller, no? Ethyl, it's hard to shift, but with methyl, it's so much slow, a small molecule can easily shift, especially if adjacent lang siya. Can do shift, but hydride also, it can shift to produce a 3-degree carbocation from a 2-degree carbocation to a 3-degree carbocation. So it's possible, and it's been documented, no, in many